So today we're going to talk about transformations in the geometric sense. And transformations in the geometric sense simply means you are moving or altering the position of an object in some manner or some way. There's a few different transformations, but the three main ones that we're going to be looking at are translations, reflections, and rotations. And each one is a different movement of an object, usually on a graph or on a grid. So if we start with this object right here, a translation of that object is simply pushing or sliding it along the graph to some different position, usually via left or right. So if I take this original picture here and I slide it to the left, that's a translation. If I slide it up, that's a translation. If I slide it up and to the left, that's also a translation. If I slide it down and to the right, it's a translation. Down to the left is a translation. So translations can get you pretty much anywhere on the graph because you're simply just taking the points and moving the object in one spot or another. No real big secret there. So a translation is a slide or a push. A reflection is a little different. A reflection is, and it's going to be kind of hard to show this on the just using a mouse and keyboard here, but a reflection is when you flip an object. So if you picture this graph as a piece of paper, you draw the triangle over on this side, you would fold the paper down the middle, and then you would kind of have an image of this marked on the other side. So it looks something like this. And if I go here and flip it, that would be a reflection. It would be flipped from one side to the other. So it's not really a push or slide. And the reason it's not a push or slide is because, as you can see, this point here would link up with this point here. So this point originally was towards the left of the shape. It's the leftmost point of the triangle. Now when I flip it, it's the rightmost point of the triangle. So reflections do not preserve the orientation of the object. Translations do. If I just slide this over here, this point is the leftmost point on the triangle, and it's also still the leftmost point on the triangle there. So it still preserves the orientation. Everything is still kind of in position relative to one another. Whereas in reflection, it does not. In reflection, it may actually change the position of the points. Um, so a reflection is a flip. Now it can be flipped left or right, or it can be flipped up or down. So by the same token, if I undo this, if we take our shape and we flip it down here, and if I flip this up and down, then this is also a reflection. I just flipped it from left and right, and I changed it to flip it from up and down. So left and right flip, up and down flip. You can actually also do a diagonal flip as well. If you kind of picture folding the paper along a crease right here, that would be a diagonal flip. That would also be a reflection. So reflections are just flipping the object around a certain line or so. All right, let's get rid of that. And then rotation is the last one. Rotations are kind of tricky because they have two different versions. A rotation is simply turning an object. So if I take this object and I turn it, this is a rotation. So if I stop here, that's a rotation. If I stopped here, that'd be a rotation. If I took the object and turned it this way, that'd be a rotation. So rotation is just turning an object. Now, it doesn't necessarily have to be about its center. So this right here, this is a rotation about the object's center point because everything is just kind of flipping around in a circle here. I could also flip it around an anchor point. So let's say that if you can picture this, and again, it's kind of hard to show on the computer program here, but if you picture each one of these points, picture them being kind of tethered to this point by a rope. So picture all these points here tethered or bound to the origin right here. I could also rotate my shape around that, and it would look something like this about. So if you picture this point anchored to this point, there's a rope connecting these 2 points, and I just turn that object here. So rotation is turning an object either about its own center or about some other point. And again, I could anchor it to this point here. I could have anchored it to this point here, or this point here, or this point here. It doesn't matter where you anchor something is. A rotation is simply when all the corners are connected to a point, and you're going to turn the object around that point. Now, other than just the general description, these each have mathematical connections associated with them as well. Something happens to the points of a picture when it's transformed. And just some terminology here, the picture we get after transformation, so after I've rotated this, this is what's known as the image. So it is an object that has been changed, and the what you get after you change it is the image of the object. So a translation, as I said before, is just pushing an object left to right, up and down, and as the simplest mathematical explanation. A translation is simply subtracting or adding numbers to the x and y coordinates. So if you move left, you subtract it from the x. If you move down, you subtract it from the y. If you move right, you add it to the x. If you move up, you add it to the y. So translations are just adding and subtracting numbers to the x and y values of the points. An easy way to remember this is if you draw a quick little sort of grid here, not really a grid, but if you draw a quick little set of axes, you can tell yourself, okay, moving right means add to the x, moving down means subtract from the y, left is subtract from the x, up is add to the y. So this little grid will help you know what to add and subtract and to where. So if you say move left 3, okay, left means subtract the x, so I'm going to subtract 3 from all my x's. Moving up 5, okay, up means add to the y, so I'm going to add 5 to all my y values. So one of the ways this looks, so we have a picture here, we have our triangle again. We've labeled the points A, B, and C, and we want to move this triangle 2 spaces left and 3 spaces up. 2 spaces left and 3 spaces up. Now, if we're given a grid, we can just kind of picture that, right? We can say, okay, C, move 2 spaces left, 1, 2, move 3 spaces up, 1, 2, 3. So this would be where C prime is. Now, the reason we say C prime is a few reasons. The prime tells us that this point is not originally there. This point was altered from some other position. The reason we call it C prime is so we know where it came from. So C prime tells you that this point has been moved from this point originally. If I just called this point D, I wouldn't know where it came from. I'd say, okay, D what? Or is it originally there? Did it move from someplace? And if I called it C, then we'd have an issue of having 2 points labeled as C, which we don't know which one is which. So C prime, C apostrophe, lets me know that this point has been moved to here. And again, we call that prime notation. So C prime just means that it's the point C that has been moved to this spot. So this is the point 1, 6, it looks like. Now, instead of moving each point individually, if I didn't have a graph or if it didn't fit on the graph, I could do it algebraically, doing what we said before. 2 units left means subtract 2 from the x coordinates. So A, point A here, 2 left means subtract 2 from the x, so my new point is 2. And 3 up means add 3 to the y. So 6 add 3 would be 9. So my new point for A is 2, 9. So it'd be right there, and that would be A prime. And if you want to check it, you can. That is 2 left and 3 up. So you can do this completely algebraically as well. Same for B. Subtract 2 because you're moving left. Add 3 because you're moving up. So it'd be 5, 7. So here's 5. 1, 2, 3, 4, 5, 6, 7. So B prime would be right there. And my new triangle would be right there. So this triangle is the new triangle I get after I move 2 up and 3, 2 left and 3 up from my original picture. So this image is what I get from altering this object in this manner. So again, you can do it by the graph, or you can do it by adding or subtracting. Doesn't matter which. You should know how to do it by adding or subtracting, though, because sometimes you might not be given a graph. By the way, some people will write this as sort of shorthand of saying this. They'll say xy goes to x minus 2 and y plus 3. This is basically the algebraic way of saying this right here. This says 2 left and 3 up, because subtract means left, so left 2, and add on the y means up, so up 3. So sometimes you might see it written like this, which is just purely algebraic form, and it's actually easier because it tells you what to do. It says take your x's and subtract 2. Take your y's and add 3. So take your x's 4, subtract 2, you get 2. Take your y's 6 and add 3, you get 9. And do that for every point. So see it like this, you get a little bit easier because it tells you outright what to do. Again, doing the negative ones is the same way. 1 right means add 1 to all my x values. So I'm just going to do that right away. Add 1, add 1, add 1. So 4 plus 1 is 5. 7 plus 1 is 8. 3 plus 1 is 4. 5 down means subtract 5 from the y. So minus 5, minus 5, minus 5. 6 minus 5 is 1. 4 minus 5 is negative 1. And 3 minus 5 is negative 2. And then once you have the points, just go ahead and plot them. So A prime is at 5, 1. So here's 5, here's 1. So that's A prime. B prime is at 8, negative 1. So that's down here. And then C is at 4, negative 2, which is right down here. And so there is my moved triangle. Again, kind of have a kink there as I'm drawing the triangle, but you have to do. All right, so, and again, translations preserve the orientation. So as you see here, if we go top to bottom, it's A, B, C. A is at the top, B is in the middle, C is at the bottom. In our new shape, we also have A, B, C. A at the top, B at the middle, C at the bottom. C is the leftmost point in both ones, B is the rightmost point in both ones, and A is the topmost point in both ones. So translations preserve the orientation of the object. The other two do not necessarily preserve the orientation of every point. Translations are special in that regard. But again, translations is just a matter of adding and subtracting. That's it. Reflections are a little bit different, although they actually are easier mathematically. But the thing about reflections is it requires an axis of reflection, also known as a line of reflection, to work. Basically, a line or axis of reflection is what we are going to be folding the paper across. So it's kind of like the crease in the fold. So if I say my axis of reflection is at x equals 2, that means I'm going to fold my paper along that line, or I'm going to put a giant mirror right on that line and see how my object reflects off of it. And again, it's called the axis or line of reflection, and it's just kind of your mirror starting point. Now, if you reflect along the x-axis, you're going to reverse the sign of your y-coordinate. If you reflect along the y-axis, you're going to reverse the sign of your x-coordinate. So kind of think opposite. Reflecting along the x means change the y. Reflecting along the y means change the x. And the two axes here are going to be our reflection lines. So there are other lines of reflection other than just these. You can have lines of reflection that go diagonal. You can have lines of reflection that aren't on the axes. But we're just going to focus on these two just to get a good start on it. So let me show you what I mean here rather than just talk about it. So here's the x-axis, right? I'm going to reflect along the x-axis. That means I'm going to take this picture and I'm going to fold my paper basically in half, hamburger style, where this would make the crease. So this is my axis of reflection, so this is the crease in my paper. I'm going to take it and fold it down. I'm going to see where this image, where this picture rather, would show up down here. Now, I can't physically do that on the computer. I can't actually physically take the paper and fold it down, nor can I slide or move it to make that same effect. So I have to rely on the math part of it. So remember, if you fold across the x-axis, you're going to reverse the sign of your y-coordinate. So I'm going to take all my x's and keep them. My x's aren't going to change. My x's are all going to be the same, but the sign of my y-coordinates are going to swap. So positive 6 becomes negative 6, positive 4 becomes negative 4, and positive 3 becomes negative 3. So if I plot these points, 4, negative 6, that's A prime. 7, -4. That's B prime. And C is 3, -3, which is C prime right there. So my new triangle would look like this. And as you can see, again, I can't draw straight lines, but this triangle is basically the flipped form of this triangle. If you picture folding the paper down from top to bottom, then you would get this little image down here. And notice that the points are now in a different orientation. So C is on the top here, whereas A was on the top in the original. So it did not preserve the orientation of the object. But that's all you do for reflections, is you find out which axis you're reflecting over and swap the sign of the opposite points. So if I'm folding along the x-axis, I'm going to swap the signs of the y, and vice versa. So if I have the same picture and fold it along the y-axis, well, not the same picture, but if I have the same shape, a triangle, and fold it along the y-axis, that means folding on the y-axis means change your x-coordinates. So -3 becomes +3. The y-coordinate stays. 0, well, 0 is neither positive nor negative, so 0 is just going to stay 0, and the y-coordinate is going to stay the same. And here, -4 becomes +4, and the y-coordinate stays the same. So I have 3, 5, which is right here. That's A. And I have 4, 2, which is right here. And that's C. I should put prime here. And so this is my reflected triangle. Now, something a little strange happens when you have points that are directly on your mirror, that are directly on the axis of reflection. Those points don't change. So 0, -3, or sorry, 0, 3 is on the line I'm reflecting over. It's on the line I'm folding across. So that point's not going to change because 0 is still going to be 0 even if you swap the sign. So if you're reflecting across something that a point is already on, then that point will not change. If your reflection axis already contains a few points, those will not change, but the other ones will. So in this case, B prime and B are the exact same point, whereas the other two are slightly different. Another way of doing reflections, just real quick here, is you can also do it by jumps. So if the y-axis is my axis of reflection, if I'm folding across the y-axis, I can count how many spaces the points are away from the y and do that same movement on the other side. So for example, C here is 1, 2, 3, 4. C is 4 jumps away. So I'm going to take this and I'm going to jump it 1, 2, 3, 4, and that gets me to where C prime would be. Same thing for A. A is 1, 2, 3 jumps away. So I'm going to do 1, 2, 3 jumps more, and that gets me where A prime is. And then B is obviously 0 jumps away, so it stays where it's at. So the jumping method is another method you can do as well if you have a graph. Again, if you don't have a graph, it doesn't help you, but if you have a graph, that's one thing you could do. And then lastly, rotations here. Rotations are kind of the trickiest one. Rotations, like reflections, require sort of a extra little tidbit. They require what's called a center of rotation. As I said before, a center of rotation is simply where are all your points anchored to? Where is the key point that you're going to be spinning your object around? So I usually call that the anchor point. And we're going to work with the origin as our center of rotation for all our rotations because it's a good starting point and anything else requires a little bit of trig to work out. So we're going to picture us rotating an object about the origin. So every time we have a picture on the graph, think about all those points are connected to the origin by a tether or by a rope or by a line, and we're going to spin it around the origin. And there's 3 different degrees we're going to look at, 3 different degrees of spin. 90 degrees clockwise means reverse the sign of your x and then swap your x and y coordinates. So what that means is that you have a point here that is x, comma, y. If you do 90 degrees rotation clockwise, your new point would be y, comma, negative x. Let me show you by a number here. So let's say I have the point 2, 5. A 90-degree rotation clockwise would mean that I have the point 5, negative 2. So I take the sign of my x, I reverse the sign, so 2 becomes -2, and then I swap the points. So -2 is now the second point, and 5 is now the first point. 90 degrees counterclockwise is just the reverse. If you have the point xy, you now have the point -y x. So you you reverse the sign of your y, and then swap your coordinates. So again, if I have the point 2, 5, and I rotate 90 degrees counterclockwise, +5 becomes -5, and then swap your points. So -5, 2. So these are tricky because they have 2 steps to them, and it's a little bit hard for some students to remember which one is the x one and which one is the y one. So it just takes a little bit of practice. So clockwise, reverse your x and then swap. Counterclockwise, reverse your y and then swap. And the last one is 180 degrees. 180 degrees is basically a super reflection. So in a reflection, you swap the sign of one of the coordinates, right? We just did those. In a 180 degree rotation, you swap the sign of both. So if I have the point 1, -4, a 180 degree rotation would make me the point -1, +4. I just reverse the sign of every coordinate in the point. That's it. So it's like a super reflection. And it doesn't matter whether you go clockwise or counterclockwise for 180 degrees, you're going to wind up at the same point. So that's why we don't have a clockwise or counterclockwise notation here. So let's try one here. 90 degrees clockwise. So clockwise means reverse the x and then swap the coordinates. So 4, 6. Reverse the x, make that -4, and then swap the coordinates. So I'd have 6, -4. Reverse the x, -7. Swap the coordinates, 4, -7. Reverse the x, -3. Swap the coordinates, 3, -3. So how would this look? Well, we have 6, -4, which is right there. That's A prime. We have 4, -7. That's going to be about right there. That's B prime. And then we have 3, -3. So 3, -3. That's right there. That's C prime. So this would be the new triangle I get. And as you can see here, that's, again, if this point is tethered to the origin, if I rotate that point, if I swing that point around, it makes sense to go about it. That's about a 90 degree angle right there. That's 90 degrees of rotation from C to C prime. If you want to measure that, you can, but that is a 90 degree turn. Same thing for all the other points. A swings around to A prime, that's 90 degrees, and B swings around to B prime, that's also 90 degrees. And again, the orientation is messed up again, because C was on the bottom, now it's the highest point, it's the topmost point. So rotations do not preserve the orientation of the objects. If we do counterclockwise, same shtick, just different points. So reverse the y, and then swap the coordinates. So reverse the y, -6, swap the coordinates, -6, 4. Reverse the y, -4, swap the coordinates, -4, 7. Reverse the y, -3, swap the coordinates, -3, 3. We'll see how this looks. We have A is -6, +4. That's A prime. B is -4, +7. So that's B prime. And then C is -3, +3. And there we go. That's C prime. And again, if you picture a tether here, if I swing it counterclockwise, I can't really draw a good line there, but that is also a 90 degree angle right there. So that's a 90 degree turn from each point. So again, counterclockwise, reverse the y first and then swap. Clockwise is reverse the x first and then swap. And lastly, 180 degrees is the easiest one because all you do is you switch the sign. There's no swapping. It's the rotation that you don't swap points in. Everyone else you do, but 180 you don't. In 180, you just take the positives, make them negative, take them negative, and make them positive. So These are both positive, so down here they're both going to be negative. Both positive, both negative. Both positive, both negative. And again, if one of my original points was negative, I make them positive, but all my original points are positive, so 180 degrees means they're all going to be negative. So -4, -6, there's A prime. -7, -4, there's B prime. And -3, -3, there's C prime. And again, that's if I anchor this point right here, that's a 180 degree rotation to my new point. And it doesn't matter if I do 180 degrees this way or if I do 180 degrees that way, it's still going to end up at the same spot. So all you do is you swap the signs of all your coordinates. So these are the 3 basic transformations on how to do them. Again, rotations are probably the hardest to understand because they have 2 steps to them, and it's kind of hard to link which step goes with which degree and which direction. But the more you practice, the easier it comes. Hope you enjoyed the video. Have a good day.